Hi everybody, this is another video on Calculus 2. This time we study section 6.5, length of curves. So pretty much what we're trying to find is the length of the curve, and the curve is given by a function, and that function has the characteristic that is not only it is continuous, it has the first derivative that is also continuous. So it has a continuous first derivative. And why do we need the first derivative? We'll see that in a moment. But the function has the continuous first derivative on the interval a to b. So pretty much we only find the arc length from a to b, and it says that the length is given by this formula here. So of course, because we have the derivative there, so that's why we need to have a continuous first derivative. Right. So where's that come about? So let's look at this. Is the function y equal to f of x, and we go from a to b, and the concept of calculus, just like what we do with the area, what we do with the volume, we're going to cut that segment cut that length into a bunch of little segments, and each one of them, even though it is a curve, we can estimate using a straight line. So, and that's what we zoom in on that part. I'm going to draw that over here. And for one segment like this, we turn into that. So what we're trying to find is the length of that curvy segment, and that is approximated by this length here. And since that is for a very small segment, we call that ds. And add over them up, we have the length of the whole thing. Right, now, in that, when we have a draw a triangle like this, there will be the change in the y values, the change in the x values. Here we use delta y, and here we use delta x. If we take that to be extremely small and take the number of segments go to infinity, so delta x and delta y become extremely small. So we just say dx and then dy. A change in x and change in y becomes dy and dx and dy respectively. Right, now this is a right triangle, so we have ds square equal to dx square plus dy square. Right, now take the square root on both sides, and we don't need the plus or minus here because we only need the positive values. So ds is equal to dx square root of dx square plus dy square. Right, what we do next is try to manipulate this. What we do is I'm going to divide by dx square, and when we divide, we have to multiply. Right, now when we take the square root of a product, we can take the square root of that and then square root of that. So first the square root of dx square over dx square, and then dy square over dx square. So we say dx square over dx square plus dy square over dx square, and then multiply, and then the square root of dx square. Dx square over dx square, so it's 1. Now dy square over dx. Now without the square, dy over dx is the derivative, and now we just have the square. So we can just say dy over dx square. Right, and then square root. Usually it is absolute values, but if we consider dx to be positive, then we don't really need absolute values. We just say dx. And now that is the derivative. Derivative square and then time dx, and so this is ds, so the length of one segment. So if we want the whole, find the whole thing, the whole length, we just do the integral, and we'll get back to that. Pronoun with space, but I'm going to write that here. So L is equal to integral of each little segment, and that is integral of 1 plus f prime of x square dx. Of course, go from a to b. Yeah, so that is the proof. So pretty much we just find derivative and then square plus 1 and the square root and integrate. Now it's easy to set, it is easy to set that done, because that integral quite often that not, we cannot integrate it, or if we, even though if we can, it's going to be extremely complicated. We'll see it in a moment, but let's look at first rather simple example, but also try to write very small here, because it will take a lot of space on this example. Right, so I'll find the length of the curve. So we have a function on the interval 0 to 4. So we have the limit, the function, simple enough, the formula is there. Yeah. So, right, so the formula is here, obviously. And this is how the formula works. So just take derivative and then put in the formulas, and hopefully everything is easy enough to do. Right, so first I'll take derivative. I said I will write very small. Will be x 3/2 x to the 1/2 simple enough, right? Take down 3/2 original power minus 1, and then later on, since we're going to take the square root of that is not multiplying, so let's just do semicolon 1 plus derivative square be 1 plus 3/2 x to the 1/2 square be square root of 1 plus 3 square is 9, 2 square is 4, and x to the 1/2 square, 1/2 times 2 is going to be 1, so we just have x. Right. Bottom line is the length is equal to integral. I just write the formula first. A to b 1 plus derivative square now we do have the limits going from 0 to 4, and that square root is this. Right, so just need to integrate this. Simple enough. In fact it is, but it's not that difficult to do, just a bit tedious. Right, so we do this, we use substitution rule, substitution SUB 1 plus 9 over 4x. And let's take the derivative and solve for dx. derivative is 9 over 4. Cross multiply 4 du equal to 9 dx, and divide by 9, so we have 4 over 9 du equal to dx. And that's what we have for dx. Now we have the limits. This is for x go to 0, x go to 4. Right, u is equal to 1 plus 9 over 4 x. When x equal to 4, u equal to 1 plus 9 over 4 times 4. 4 and 4 cancel out, so that is 10. And when u equal to 1, when x equal to 0, u equal to 1. So this is 1 to 10. And with that, we can substitute into our problem. Now the limit, instead of go from 0 to 4, it will go from 1 to 10, and that is the limit for u. Then we still have square root, where we let inside the square root be u. And then dx is 4 over 9 du. And that is a constant 4 on the top, 9 at the bottom. So we have 4 over 9. Square root of u, we can say u to the 1/2 du. And then we have 4 over 9. Integral of that is u to the increase the power by 1 and divide by the same thing. Integrate from u equal to 1 to u equal to 10. Now divide by fraction is multiply reciprocal. 2/3. U to the 3/2, going from 1 to 10. Right, that gives us 8 over 27. And then put 10 in for u. Now let's just write like this first. Then put in 10 and then put in 1. 8 over 27. 10 to the 3/2. Subtract 8 over 27. 1 to the 3/2. And 1 to the 3/2 is just 1. And 10 to the 3/2, we just have to leave it like that because we cannot simplify it. Or 10 square root of 10 if you want to, but I will just leave 10 to the 3/2. Right, let's use a calculator to check the work. Right, never mind. Math number 9, going from 0 to 4. And we have square root 1 plus 9 over 4. 9 over 4x dx. So that, how about we enter like this, h alpha y equal, that gives us a fraction, alpha and y equal, and then times 10 to the 3/2 minus 8 over 27. Yeah, of course. That should be the same thing. Alright, now, even better. Just want to show you that calculator can even do calculus approximately. So if we enter the function x to the 3/2, right? Now, we enter the formula exactly as we see it. Here we have the square root 1 plus. We haven't taken derivative, but if we want to, we can find derivative like this. Open parentheses, math, and the derivative is option number 8. We're going to take derivative with respect to x. Hit variables, y variables, and y1. So either we do that, or you can hit alpha, calculate, the bottom menu pop up, so alpha, trace. So we take the derivative of the function y1 with respect to x when x equal to x. So we just enter like this. And then remember we have the derivative. Sorry. The derivative square. Alright. Okay. It may not be exact, but they're pretty close. Because like I said, the calculator can only do approximation. Right. Bottom line. Yeah, the formula is straightforward. Not difficult to prove either. But the integral though sometimes would be very complicated. You see that in the next example. Right. Now, I'll find the length of the curve. That is the curve on the interval 1/2 to 2. Right. So, of course, just like we did earlier, we take the derivative and then put in the square root of 1 plus derivative square. That's simple enough. Yeah, but so we take derivative. Yeah, the number here might not be very friendly. Right, derivative of x cubed 3x squared. Derivative of this, if I rewrite the function as a power, I can say 112, and then x from the bottom to the top become -1 power, and derivative of that, take the negative down, and original power -2. Right. So how did that help us? Now we're going to put in the formula 1 plus derivative square, right? Now let's just square this and see what happened. By the way, I will rewrite this first. I move the x squared down to the bottom. And do the common denominator. The top 3x squared have to multiply by 12x squared. So the common denominator is 12x squared, so I have to multiply that. And then -1. Right, that gives us 36. X to the 4th -1 over 12x squared. Right, so that is the derivative. Now what we need is the square root 1 plus derivative square. If it turns out better, then it might help, but it looks complicated for now. 1 plus the derivative square. All right. So we square the top and square the bottom. Square the bottom will be 12 square, will be 144. I'm just going to say 12x square. And square of the top, square is multiplied by itself. Even though I write very small here, but I don't think will fit on the problem here. But at least we have to see where the end of the line at the end of the tunnel, so to speak. Right. So that square is 144x to the fourth. So multiply 36 times 36. 1296. Times 1 minus 36 x to the fourth minus 36x to the fourth minus 1 times y is 1 plus 1 all over 144 x to the fourth. Right. Combine like terms, common denominator. I'll multiply 144 x to the fourth top and 144 x to the bottom, x to the fourth at the bottom. And then we add 144 x to the fourth. I forgot the x to the fourth times x to the fourth, x to the 8. So we have 1296 x to the 8 minus 36 minus 36 is minus 72 x to the fourth plus 1. Now the bottom is 144 x to the fourth. The top we just have those three things. 144 x to the fourth, 1296 x to the 8 minus 72 x to the fourth plus 1. Combine like terms, namely this 144 minus 72. 144 minus 72 is plus 72 x to the fourth plus 1. 144 x to the fourth. So how did that help? Now take a look at this. Pay attention on these three terms here. That one is equivalent to this. Or equivalent to that one square. Notice that when we multiply it out, it will be minus 36 minus 36, ultimately give us minus 72. Now what instead of that, we have this term instead. But it is a plus. instead of the minus. So notice that if it is a minus, will come from those minus here, and if it is a plus, so those two will be plus. In particular, what we have here is, if we have a minus b squared, it is going to be a squared minus 2ab plus b squared. But if we have a plus b squared, still a squared, but it's going to be plus 2ab. So notice that if this is a plus, it will be a plus. If it is a minus, it will be a minus. And those coefficients, everything will stay the same, just different size here. So when we have a plus here, that will be equal to square root of, those are the square, right? So we say 36 x to the 4th plus 1 square over 144 x to the 4th. And we will write that as square root 36x to the 4th plus 1 square. That we can write 12x square. Square cancel out the square root. We have 36x to the 4th plus 1 over 12x square. We will split this out. 36x to the 4th and 12x square plus 1 over 12x square. And 36 over 12 is 3x square, and then we have 1 over 12 x to negative 2. So pretty much that. And bottom line, like I said, we will not have enough space to do this problem, but at least we write out the integral from 1/2 to 2 of 1 plus derivative square, which will be equal to integral 1/2 to 2. We're going to use this 3x squared plus 1 over 12 x to negative 2 dx. Run out of space here, but at least we can get to a power rule, and the rest will be simple. Yeah. So the complicated part is here, binomial expansion here. But I said when we get to this step, it will be easy because that's just power rule, and we can go from there. Yeah. I said most of this problem is that complicated because of the square root, and there's the plus here that makes things very complicated. Right. So similar to previous section where we have x, in terms of dx, we can also have in terms of dy. In that case, the formula is still the same thing. The limit for y, and then we have that. So everything is still the same. Right. Now, for this example, find the arc length of this curve from 0 to 8. Of course, we can do it like that, or if we want to, change that to y, because the formula is right up there, so it would make sense if we actually use the formula in terms of y. So it's no problem. When we have y equal to x to the 2/3, equivalently we have x to the 3/2. So let me write this again. Y equal to x to the 2/3, interchangeable x equal to y to the 3/2. Why is that? Because when we have y equal to x to the 2/3 to begin with, we can raise both sides to the reciprocal power. X to 2/3, x to 3/2, those cancel out, and we just have x and y to the 3/2. So since we use y, we're going to use that. Now, the limit, originally x go from 0 to 8. Equivalently, y will go from 0 to 4. Those are limit for x. These are the limit for y. So the arc length, I'm going to write out. Either if we want to, we can go from 0 to 8 of 1 plus derivative in terms of x. So I say x 2/3, take derivative, and then we square if we want to do dx. Now if we want to do it in terms of dy, it's going to be 0 to 4 and the function, instead of x to the 2/3, we're going to use y to the 3/2, and we take the derivative of that. And dy. So either way, if we can use x, we can use y. Make sure the limit are for x and y, and then the function, make sure the variable must be the same as the dx or the dy. Right, so now we're going to use this. So it's going to be 0 to 4, 1 plus y to the 3/2 will be 3/2, y to the 1/2 square, and then we have 1, 3 square is 9, 2 square is 4, y to 1/2 square is y, and so we have that. The reason that in this case we change to y, because earlier we did that, right? So integral of that one from 0 to 4 of that is equal to this answer. So I'm just saying this equal to just going to copy 8 over 27, 10 to the 3/2 minus 8 over 27. And the reason we can say that is because we already did it. So see example 1b. And we already did that. Right. However, I just want to do that in terms of x and see what happened. Kind of nice to do. So I'm gonna go from there. Derivative of this is 2/3 x to the negative 1/3 square. Right. Yeah, I just want to say, if this is the case, we do that directly, what can we do? 1, 2 square is 4, 3 square is 9, x to negative 1/3 square is negative 2/3 dx. Right. Now, and this move to the bottom. And then do the common denominator. going to put that here. Yeah, from there. Multiply that to the top. 9x to the 2/3 plus 4 dx. Now split the square root. And then square root at the bottom. And then we will have square root of 9x to the 2/3 plus u. Square root of 9 is 3, and square root of x to the 2/3. So if we have x to the 2/3, square root is equivalent to 1/2. 2 and 2 cancel out. So we have x to the 1/3. Right. So we say, how does that help? Actually, it helps a lot. If we let u equal to this, du will cancel with this one nicely. So from here we let u equal to 9x to the 2/3 plus 4. You can always continue from there, but I just want to show that if this one we have to do it, this is going to how it goes. Use substitution from here. It's not that bad because it will cancel out with the extra 1/3 here. So that will work out nicely. But if we convert this to y, that integral is exactly like the integral we have earlier, but earlier we have x, here we have y. Changing the variable like that, we still have the same thing. Right. As you see, most of this from the integral is kind of complicated to do. So, I said. We don't have a lot of, I should say, reasonable example, because most of the examples are complicated like that. Right, now, find the length of the curve on the interval. Write the integral only, and then use the calculator to estimate the integral. The reason we have to use the calculator because if we do it by hand, the solution is going to be more than 1 page long, and we don't have all the techniques, we do not have all the tools at the moment. Right, so simple enough. Arc length, now we know from 0 to 2, square root of 1 plus derivative square so it is integral from 0 to 4, 1 plus derivative of x squared, that's just 2x. Yeah, so pretty much that. Two squared is 4, x squared. Like I said, even though it looks simple, but to do this, we don't have enough tool at the moment. So we just estimate using the calculator here. Option number 9 goes from 0 to, I don't know why I write 4, but it is 0 to 2, right? Sorry, I put 2. 2 square root 1 plus 4x squared ax. Right, and we have 4.65. Let's just say it. Approximation using calculator, because we cannot do that by hand. Next, write the integral and then use the calculator to estimate this. So we have the function and the arc length, the length of the curve. We have from 0 to 3/2. One plus derivative square and derivative y equal to sine x, sine 3x, derivative will be equal to cosine, derivative of sine cosine, and then there's a 3, there's we have 3 cosine of 3x. And we just have to use a calculator here. 0 to 3 half. 3 pi over 2, sorry. Three pi over 2 square root 1 plus 3 cosine 3x square. If we use a calculator, we will have about 10.48. Like I said, just do the approximation here. Next we have application problem. Now that is the function, and then look like we have to take the derivative of that, which I don't want to do. So if we don't want to do this, notice the formula in general. It's just 1 plus derivative square now this particular we have x absolute value of x less than 315, so it goes from negative 315 to positive 315. The reason of that is, in this case we have the Ridgeway arc in St. Louis. So it's next to the Mississippi River. The Gateway arc. I was there many times. So this is the symbol for connecting the east and the west of US. Anyway. So the reason that the shape like this, and so they said about 315 feet on the left and 315 feet on the right, and now we just find the arc length of it. By the way, this is parabola, so parabola that open upside down, so negative 315 and 315. Anyway, so we go from negative 315 to 315, and then here we just said 1 plus the derivative square, because I don't want to take the derivative of that quadratic function. Should be simple, but yeah, the number is not very friendly. What I do instead is I enter the function 630 times 1 minus alpha y equal to, give us a fraction of x divided by 315, square that, and close the bracket. So pretty much we have the function, right? Don't forget there's in the calculator it is the parentheses, but they understood that it is the parentheses there. Yeah, so worry about that. It did not say x squared over 315, it is x over 315 squared. That's why the square is way over there. Alright, now what we need is the integral from negative 315 to 315 square root of 1 plus derivative. Okay, math option number 8 for derivative. but we need the derivative square. Oh, shoot. Never hit that button. Once again, math number 9 for integral. 315 to 315 square root 1 plus derivative math option number 8, and derivative of the function, so alpha trace y1, we enter the function into y1 and derivative with respect to x. Let's close that and then square. So this we have the derivative with respect to x square, and I'll just have x here and wait for a moment. $1463.74, and that look like in feet. So they said the base is 630 feet. Then the arc length, the length, is going to be about 1463 feet. Look reasonable. Right. So with that, we finish section 6.5. As always, thank you for watching.